Welcome back. This is part 2 of chapter 3.6. This is the chain rule, and we're going to just look at some more advanced problems today and some applications of the chain rule. So I'm in your notes packet. Hopefully you've already watched video 1. That is how to do the chain rule and where it comes from. And we are on page 6 of your notes packet. And just to let you know, I'm going to skip 13, 14, 15. I'm going to hop to the next page. I will come back to those at the end, but I would like to show you some applications of the chain rule beyond just more complicated problems of the chain rule. So example number 1 on the next page, page 7, says find the equation of the tangent line y equals square root of 5 plus x squared at the point 2, 3. Now, we know in order to find an equation of a tangent line, we need a point, which we have, and we need slope. So we are going to find the derivative. So before I find the derivative, I am going to rewrite that function with my square root represented as a rational exponent. And now I am going to differentiate y. So my 1/2 comes to the front, my 5 plus x squared carries down, my power drops down to a negative 1/2, and now I am multiplying by the derivative of the inner function, which is 2x. So I'm going to clean this up a little bit. So 1/2 times 2 is 1, so that cancels out. I have an x on top, and then I'm going to push this into the denominator because it's a negative exponent. And that is raised to the 1/2 power, so that is inside a square root. So I now have my derivative, and I know that in order to find slope at a very specific point, I need to evaluate my derivative at this point. So I'm going to substitute in my x value. So y prime equals 2 over the square root of 5 plus 2 squared. And I'll just come up here. We're going to have y prime equals 2 over, my pen's dying, the square root of 5 plus 4, which is 9. So that gives me 2/3. So now I know my slope is 2/3. I know my point is 2, 3. So we can write an equation of the tangent line. So y minus 3 equals the slope of 2/3 times x minus 2. Okay. Next example is asking you to find the coordinates of all points on the curve at which the tangent line is horizontal. So when the tangent line is horizontal, that means the slope is 0. So my plan is I'm going to find the derivative, which is a function that represents slope of the tangent line at any point on the curve, and then I'm going to set that formula equal to 0 and find my x values. So we've got f of x equals cosine of 4x. The derivative of cosine is negative sine. The angle stays the same. And then I'm going to multiply by the derivative of the inner portion, which is my 4. Okay, so if you want to clean that up a little bit, you certainly can. We can pull that 4 out to the front. And at this point, I know that I'm looking for the points where my slope is 0, so I'm going to substitute a 0 in on the other side. And we're going to solve a little trig equation, your favorite. All right, so we're going to divide by this coefficient in the front, so that leaves me with 0 equals sine of 4x. And think about your unit circle, right? So we're looking for where is sine equal to 0. And so sine is going to be my y coordinate. We know that already. So one example of where sine is 0 is 0. The other example is over at pi. So you could name this as 0 plus 2 pi and pi plus 2 pi, and that will cover all of our angles. Or you can start at 0 and add pi, add pi, add pi, and that is a more concise way to name all of my angles. So I'm going to go ahead and name it that way. So one thing you want to realize is, when we solved this equation, we're really taking the inverse sine of both sides. I tend to skip this step, but you are certainly welcome to write it if you want. But you need to realize that we are solving for the angle, and in this case, the angle is 4x. So when I found the inverse sine of 0, we got 0 plus pi plus pi plus pi. So that is the same as 0 plus pi n. And yes, you can write just pi n equals 4x. And that covers all of my solutions. And then I'm going to divide through by 4. So I am left with pi over 4n. And they're asking for the coordinates of all the points on the curve. If you are an IB student, IB will ask you to find points within a certain domain. If you're not an IB student, you would just leave it in this format. If they asked you to find the full coordinates, though, you'd have to plug a number in and then find your corresponding y value. So let's just pretend we wanted to find the first couple solutions. So if I was going to make a list of solutions, I am methodically substituting numbers in for n. So if I substitute 0 in there, my first answer is 0. If I substitute a 1 in there, my next answer is pi over 4. A 2 in there, 2 pi over 4, which is pi over 2, etc. So if I were finding individual coordinates, I'm substituting 0 back into my original function. So that would be f of 0 equals cosine of 4 times 0. So that is cosine of 0. Let's come back over here. Cosine of 0 is 1. So f of 0 is equal to 1. So there's one example of a point. We'll go ahead and find one more. So let's say we were going to find pi over 4. So I'm substituting pi over 4 back into my original function. So cosine of 4 times pi over 4. So my 4's cancel. So cosine of pi, so I'm over here. So cosine would be -1. So my point would be pi over 4, -1. Okay, so there's two examples of coordinates. There are technically an infinite number of points, so we won't list them because we'll be here forever, literally. Okay, example number 3. Suppose that W is defined as U composite V. Please note that's not a product, that is a composition. So W equals U of V of X. And they're defining U of 0, V of 0, U prime of 0, U prime of 2, V prime of 0, and V prime of 2. And they want you to find V prime of 0. So before I can look for W prime of 0, excuse me, before I can look for W prime of 0, I need to find W prime. So if in order to find the derivative of a composition of functions, that means I have to use my chain rule. So I'm going to start by taking the derivative of the outer part times the derivative of the inner part. So the derivative of the outer part would be U prime. The inner part stays the same, times the derivative of the inner part, which is V prime of X. And folks, you might recognize this. This is actually the formal definition of our chain rule. But in your notes packet, when we looked at this earlier, it was written as f of g of x. All right, so we've now expanded that to represent w prime, and what I'm really finding is w prime of 0. So everywhere that I see an x, I'm going to substitute a 0 in here. So u prime of v of 0 times v prime of 0. And I'm going to kind of work my way out from the inside. So v of 0, let's look at our list of pieces of information that were given to us. V of 0 is 2. And now I'm looking for u prime of 2. We were given that as well. So u prime of 2 is 4 times v prime of 0, which is 5. So 4 times 5 is 20. Okay, so there's an application of a chain rule where they handed you the information in a list form. The next example we're going to look at is very similar, but our data is going to be given to us in a tabular form. So let's take a look at example A, and I'll just show one example for our video purposes. So f of x is defined as f of x. And they want us to find f prime of 2, which means I need to start by finding an expression for f prime of x. I like to find a very generic, more general form of my derivative first. So I'm expanding this using my chain rule derivative formula. So I grab the derivative of the outside times the derivative of the inside. So the derivative of the outside is f prime, the inner part stays the same, times the derivative of the inner part, which is f prime of x. And now we are finding the derivative at 2, so f prime of 2. So everywhere that I see an x, I am going to replace it with a 2. And instead of us grabbing information from the original problem, we're just going to grab our information from this table. So starting from the inside here, f of 2, so here's my f column, here's where x is 2, so f of 2 is 1. And now I'm going to find f prime of 1 and f prime of 2. So f prime is my column here, f prime of 1 is 4, f prime of 2 is 5. So we have 4 times 5, which is 20. Okay, I'm going to skip that last example on there, but it's done in the same way. Take a look at the last example on this page, example number 5. If f is the function whose graph is shown, let h of x equal f of x and g of x equal f of x squared. Use the graph of f to estimate the value of each derivative. So we saw an example where your data is given to you in a list format. We saw one where it's given to you in a table format. Now we're looking at one where we're going to have to extract data from a graph. So they are defining h of x as f of x. And they want me to find h prime of 2, sorry, delayed reaction there. They want me to find h prime of 2, so I need to start with h prime of x. So I'm just going to expand the chain rule here. So derivative of the outside would be f prime, the inside stays the same, derivative times the derivative of the inner part, which is f prime of x. And now I'm finding specifically h prime of 2. So I'm going to replace all of my x's with 2. So f prime of f of 2 times f prime of 2. And now when you're needing to find data, I'm looking at my graph. So f of 2 is saying when x is 2, find the y coordinate. So I'm going to come over here. This is my graph of f. When x is 2, my y coordinate here is -1. So that's the point 2, -1 right there. So f of 2 is -1. Now I need to find f prime of -1. That means at -1, you're looking for the derivative, which is the slope of the tangent line. So my tangent line would actually be sitting right on that same line, and that slope is 1 over 1. So the slope at -1 is 1. And then I'm being asked to find the slope at 2. So here's 2 over here, but I'm not looking for the y coordinate. I'm looking for the slope, and this is my tangent line. So I'm just going to grab any 2 points on there and find my slope. So that would be down 2, right 1. So that would be a slope of -2. So last step, we'll multiply those. 1 times -2 is -2. I'm going to go ahead and do this last one. So we have g prime of -2. So the first thing I want to do is identify what g of x is. So they're defining g of x as f of x squared. Okay, so the derivative of g of x would be the derivative of the outside part, which is f prime. Inside part stays the same, times the derivative of the inside part, which is 2x. So this one's a little bit different because it's not a function notation on the inside, it's actually the function. Okay, so what we're going to do is we are looking for the at this point, not g prime of x, let's actually substitute what x is. So we are finding g prime of -2. So I'm going to substitute -2 in everywhere where I see an x. So we have f prime of -2 squared times 2 times -2. So on the inside, -2 squared is 4. And over here, we have 2 times -2, which is -4. And then we're grabbing f prime of 4 off of our picture. So that is the slope when x is 4. So 1, 2, 3, 4, we're over here. That got cut off a little bit, but I think that that is a slope of 1 over 2. So a slope right here of 1/2. So that would be 1/2 times -4, which is -2. Okay, so that is the end of the different types of applications you might see of the chain rule. I am going to back up If you would like to see some more difficult problems of the chain rule, I'm going to show some more examples. So I'm back on page 6. So if I were to start at the bottom, this is an example of a function in a function in a function. So when I'm finding my derivative, my outer function derivative of sine is cosine. The inner part stays the same, times the derivative of this middle part here. I'll do this in pink. So the derivative of cosine is negative sine. The inner part stays the same, times the derivative of the innermost part, which is 3x plus 5. So its derivative would be 3. So really the only thing you can do here, you can multiply this 3 times that negative and pull that way out to the front. So negative 3 cosine of 3x plus 5 times sine of 3x plus 5. Okay, so there's an example in the form of f of g of h of x. Function within a function within a function. All right, I'm going to back up and take a look at example number 14. So we have a function built into a power. So no need to rewrite. This is ready for me to take the derivative. So I'm going to pull my 5 out to the front, and I'm going to keep the inside portion the same. I'm going to drop my power from 5 to 4. But now I have to multiply by the derivative of this entire intersection. And that is a quotient, which means I am going to be doing the quotient rule. So I'm going to do low d high minus high d low over low squared. So low would be 5x squared plus 9. D high, derivative of 6x minus 4 is 6. Minus high, which is 6x minus 4. D low, so the derivative of the bottom is 10x. And that is all over low squared, so that is 5x squared plus 9. Okay, so we're going to try to clean this up a little bit. So what are we going to do to clean this up? First thing, I'm seeing that I have a 5x squared plus 9 down here and down here. So I can combine those, but first I have to apply this 4 to both the numerator and the denominator. So I'm going to separate this. So that would be 6x minus 4 to the 4th over 5x squared plus 9 to the 4th. And then over here, on the bottom, we've got 5x squared plus 9. On the top, you know, if anything, I could factor out a 2 maybe. So I'm just going to distribute and add like terms. So we would have 30x squared plus 54. And then I'm going to distribute this subtraction symbol to the 10. So we would have minus 60x squared plus 40x. Okay, on my next step, I am going to combine all of these into one big fraction. So I have a 5 on top. I have a 6x minus 4 to the 4th. And I have 30x squared minus 60x squared is negative 30x squared plus 40x plus 54. In the denominator, I can combine these. So we have 5x squared plus 9 to the 1 power. Oh, I'm just realizing when we took my quotient rule, low d high minus high d low over low squared, I forgot the squared on there. There should be a squared on there. So now what we have is I'm going to combine these by adding their exponents. So 5x squared plus 9 to the 6th power. And if anything, we could factor a 2 out, but you could leave it like that. If you factored the 2 out of here, that 2 would join the 5 out in the front. So you'd have 10 times 6x minus 4 to the 4th. So that would become negative 15x squared plus 20x plus 27 all over 5x squared plus 9 to the 6th power. Okay. All right, I'll show one last final example just in case you want to see it. I don't know that you have any in your homework quite like this, but here's an example. So we've got a chain rule on top, function and a function, chain rule on the bottom, function and a function, but the bigger picture is that this is a quotient rule. This might look somewhat familiar. In the lesson video filmed before this one, we had a quotient rule way at the bottom. So this is just a variation of that quotient rule, which is why I left it for the last example in our notes packet, because you've already seen one sort of like it. So I am going to find my derivative by starting with the big picture, which is the quotient rule. So low di, so low is 3x minus 8 to the 5th power. D high is a little chain rule. So the 2 comes to the front, 2x plus 3 carries down, power drops down to a 1, times the derivative of this inner part, which is 2. Low d high minus high, 2x plus 3 squared, d low. So the 5 comes to the front, 3x minus 8 carries down, power drops down to a 4, times the derivative of the inside part, which is a 3. And that is all over low squared. So that is 3x minus 8 to the 5th squared. Okay, the derivative part is actually the easy part. It's probably cleaning it up where you might run into some trouble. So the first thing I'm going to do is actually just clean up the coefficients. So 2 times 2 is 4, times 3x minus 8 to the 5th, times 2x plus 3. Over here we have 5 times 3, so that's minus 15, times 2x plus 3 squared, times 3x minus 8 to the 4th, all over 3x minus 8 to the 10th power. And I'm going to continue on with simplifying this. I'm not distributing this out. That would be ridiculous because we have a 5th power and a 4th power. But I am going to look at the bigger picture, and I'm seeing that these two big terms have common binomials. They both have a 2x plus 3. They both have a 3x minus 8. So I'm going to factor out to the front what I can. And what I factor out to the front, I will do in green here. So it looks a little different. So whenever I factor out a binomial, 3x minus 8, I can factor out the smallest power. So I'm going to factor out 3x minus 8 to the 4th power. And then I'm going to factor 2x plus 3 out. And the smaller power between 2 and 1 is 1. And then I'm going to write what is left over after I divide. And I still have this denominator of 3x minus 8 to the 10th power. So when I divide, this first term divided by this greatest common factor, my 4 carries down. 3x minus 8 to the 5th divided by 3x minus 8 to the 4th leaves you with 3x minus 8 to the 1 power. My 2x plus 3 divided by itself divides to equal 1, so that's gone. Minus, now I'm dividing the second term by the greatest common factor, so minus 15 carries down. 2x plus 3 squared divided by 2x plus 3 to the 1 is 2x plus 3 to the 1. 3x minus 8 to the 4th divided by itself is 1, so that cancels out. Close that off. And all I'm going to do now is just clean up what is inside here. I'm also seeing that we have a 3x minus 8 and a 3x minus 8. So when you have the same binomial, this numerator is in a factored form. So these 4 terms will simplify with 4 of these. So 10 minus 4 will actually leave me with a power of 6 in the denominator. So we will have in the front 2x plus 3. In the brackets, we'll have 12x minus 32 minus 30x minus 45 all over 3x minus 8 to the 6th power. And I'm going to go one last step. I'm just going to go over here to the right, see if I can squeeze it in, and I'm going to add these like terms. So we would have 2x plus 3. 12x minus 32x is going to be negative 18x. Negative 32 minus 45 is negative 77. And that is all over 3x minus 8 to the 6th power. That is the most simplified this expression could possibly be. Okay, so you've seen about every variation I could possibly ask you of the chain rule. Thank you so much for listening. Bye-bye.